Welcome to our discussion of substitution and elimination reactions in synthesis. We're going to talk about this topic as well as specific topics about synthesizing an ether, synthesizing an alkene, and some particular things we need to remember about substitution and elimination. And we're going to look at some examples of designing a synthesis. So let's go to the next slide. Substitution and elimination reactions in synthesis. Earlier, we learned that nucleophilic substitution reactions of alkyl halides can lead to a very wide range of organic compounds. Here we have Williamson ether synthesis reaction that has an alkyl halide reacting with an alkoxide ion. Here's the alkyl halide and the alkoxide ion forming the ether. The alkoxide ion, illustrated as R with an oxygen negative, is prepared by using sodium metal or sodium hydride to remove a proton from an alcohol, as you can see illustrated on the slide. So the next thing we need to look at is the Williamson ether synthesis is a nucleophilic substitution reaction. It's an SN2 because it requires high concentration of a good nucleophile. This slide shows two ways to synthesize butyl propyl ether. Depends upon the starting material. So you can see these two examples. What would be the reactants needed to be if you wanted to synthesize something a little different, like tert-butyl ethyl ether? Of course, if you look at this closely, you realize that you're going to need ethyl halide and a tert butoxide ion. And we're going to look at that on the next slide. But first, if you look at this one, two ways to synthesize butyl propyl ether, you'll notice that there are 3 carbon atoms in this compound, 4 in this one, and a total of 7 in the product. Well, we could do 4 butyl group on bromine, 4 and 3 as part of the nucleophile, and also arrive at 7. And notice it's still butyl propyl ether in both cases. So let's take a look at synthesizing tert butyl ethyl ether. If you use a tert butyl halide, as in the second reaction above, right here, an ethoxide ion as reactant, you would obtain the elimination product with little or no ether. This is so because the reaction of a tertiary alkyl halide under SN2E2 conditions forms primarily the elimination product. So in doing an ether synthesis, the less hindered alkyl group should be provided by the alkyl halide, and the more hindered alkyl group should come from the alkoxide, as in the first reaction on this slide. So here we have ether being formed, and in this case down here we have no ether being formed. We have less hindered ethyl bromide here and tert butoxide ion forming the substitution product and the elimination product. And here's ethoxide, tert butyl bromide forming the elimination product, and the product after gaining the proton from the tert butoxy bromide is shown here, the alcohol. So in synthesizing an ether, the less hindered group should be provided by the alkyl halide. However, the most hindered alkyl halide should be used if you want to synthesize an alkene. You should choose the most hindered alkyl halide in order to maximize the elimination product and minimize the substitution product. For example, 2-bromopropane would be a better starting material than 1-bromopropane for the synthesis of propene, because the secondary alkyl halide would give a higher yield of the desired elimination product and a lower yield of the competing substitution product. The percentage of alkene could be further increased by using a sterically hindered base like tert butoxide instead of the hydroxide ion that we see here. To synthesize 2-methyl-2-butene from 2-bromo-2-methyl-butane, use SN2E2 conditions, which involves high concentration of methoxy anion and an aprotic polar solvent, because a tertiary alkyl halide forms only the elimination product under those conditions. If it's SN1E1 conditions, that is a low concentration of methoxy anion and a protic polar solvent, both elimination and substitution products would be obtained. Here's consecutive E2 elimination reactions that can be used to make alkenes, which could include conjugated dienes, and alkynes. Alkyl dihalides can undergo 2 consecutive dehydrohalogenations, giving products that contain 2 double bonds. Now, not shown in the slide, we could take a reaction involving 3,5-dichloro-2,6-dimethylheptane, and we can get one that follows Zetso's rule but not a second reaction, because a conjugated diene is more stable than an isolated diene. And you would just have to write this out to see what this really involves. But if you were to take the 3,5-dichloro-2,6-dimethylheptane and react it with a strong nucleophile like an OH, then you're going to form a product according to Zetso's rule. Then the second reaction with the product that you've obtained from the first elimination reaction will give you a product that's not following Zetso's rule, because a conjugated diene will be formed. Now, back to the slide here. If 2 halogens are on the same carbon, known as geminal dihalides, or on adjacent carbons, known as vicinal dihalides, in this case, geminal dibromide and vicinal dichloride, 2 consecutive E2 dehydrohalogenations can result in a triple bond. There they are. This is how alkynes are usually synthesized. Now, on the next slide, we'll show how to convert a double bond into a triple bond using consecutive E2 elimination reactions. So here's converting an alkene to an alkyne, where we have 2-butene as our starting material. We're going to brominate the sp2 carbons, and now we can do 2 consecutive E2 reactions, as you can see here with this nucleophilic interaction, resulting in an alkene after the first one. Then a second elimination, we result in a triple bonded alkyne. Let's talk just for a few minutes about designing a synthesis and approaching the problem of doing this with 6 examples. So we're going to design a synthesis. We need to find the pathway to the target molecule by simple synthesis. This is our target. This is our starting material, a hexane. We want to produce a hexadiene. In this slide, what we want to do is form 1,3-cyclohexadiene from cyclohexane. Remember, the only reaction an alkane can undergo is halogenation. So the first reaction is easy to predict. It's going to be halogenation. Next, we need to use a high concentration of a strong and bulky base to have elimination predominant over substitution to form cyclohexene. The third step is bromination of cyclohexene. The second reaction is now repeated again. So here's the first reaction. And then this is the second reaction. We put bromine on, then we're going to undergo an elimination reaction. Here's the third reaction from this product here, the third reaction. Again, elimination, and then again we're going to form the final product with bromination here, and then the second reaction of elimination again. So we can form the target molecule. Here's a second example. Methyl cyclohexane is our starting material, and we want to make vicinal trans dihalide type compound, this target. Now in this example, we're going to take methyl cyclohexane and make vicinal trans dihalide. Since the starting material is an alkane, the first reaction must be a bromination again. Put bromine on there. Bromination leads to selective substitution of the tertiary hydrogen. So under E2, tertiary alkyl halides undergo only elimination. So there will be no competing substitution reaction. So here we're doing the elimination of bromine and a hydrogen, E2, forming our elimination product. Retrosynthetic analysis is working backward to the target molecule. Look at the target molecule and ask how it could be prepared. Work backward to the next compound, asking how it could be prepared, one step at a time. Here's example 3. Given the starting material, how could you synthesize the target molecule that's here? Strategy would be adding HBr to the alkene would form a compound with a leaving group that can be replaced by a nucleophile. So here we got HBr adding to the double bond, and now we can replace the bromine with a nucleophile, and we've now formed our product. Note that because the cyanide group is a relatively weak base, the desired substitution reaction is going to be favored over the competing elimination reaction. And here's a fourth example. How can we synthesize trans 2-methyl-cyclohexanol? Notice these are on opposite sides of the ring plane, so we call it trans, from 1-bromo, 1-methyl-cyclohexane. Strategy would be an elimination of HBr. Again, there's bromine, HBr from the reactant, forming an alkene that can add water via an electrophilic addition reaction, because we've got to get OH on there. Make sure the elimination is carried out under E2 conditions, because the tertiary alkyl halide will undergo only elimination. So there will be no competing substitution product. Hydroboration oxidation will put the OH on the right carbon. So we can string together reactions that we've learned in the past. Here's the fifth example, designing a synthesis. First, how can we prepare ethyl-methyl ketone from 1-bromobutane? Of course, this is the starting material, this is the target. Retrosynthetic analysis, we can start with the target material and think backwards one step at a time. We can, from here, we could have had a triple bonded molecule, an alkyne, on all the way back to our starting material. So from here, we would undergo an elimination reaction, then bromination reaction, and then the formation of an alkyne, then the formation of the ketone. So the synthesis would be to take our starting material, undergo an elimination reaction with a bulky base, maximizing the elimination product, brominate around the sp2 carbons, as you can see here, that sets us up for consecutive elimination reactions. In fact, there's going to be several getting to the point that we have a triple bond. And then, as we remember, through oxidation, we can form the ketone, the carbonyl group. And the last example is, how can the cyclic ether be prepared from the starting material given. To prepare a cyclic ether, the alkyl halide and alcohol must both be part of the same molecule. So we need an OH on here. So we're going to find the new bond that was formed in the target molecule and number the atoms in the ring formed by the new bond. Here's the new bond, and numbering these 1, 2, 3, 4, 5. Addition of water to the starting material will create the required bifunctional compound which after deprotonation will form the cyclic ether through an intramolecular reaction that we've seen before. So there's the intramolecular reaction. Nucleophilic site to the electrophilic site brings this around, and we form the cyclic compound. That concludes our discussion of synthesis.